Hello, everyone, and welcome to lecture 14 of GPU computing. Today, we're going to be talking about a new pattern, which is merge. So before we start, last time we looked at the histogram pattern, and when looking at histogram, we introduced a new feature, which is atomic operations, and we also looked at a new kind of optimization, which is privatization. We said that a histogram basically approximates the distribution of a data set by finding the range of values in this data set that falls into each one of a set of bins. And an example of that we looked at during class was a color histogram, where an image is essentially a set of 8-bit pixels. So each pixel can have 256 different values. So we basically have 256 different bins, and we count in each bin the number of pixels that have the corresponding value. Now, having said that, we observed that if we want to implement something like this, where different threads are processing different input pixels and they're incrementing the same bin, we have the problem of data races. And data races occur whenever there are multiple threads that are concurrently trying to update the same location. Or more precisely, when we have the same memory location is currently accessed without ordering, and at least one of these accesses is a write. And we saw that, if I have a thread that's doing load, add, and store, and another thread that's doing load, add, and store, depending on how the instructions of these threads are interleaved in time, we may have this outcome could be 2 or it could be 1. And for example, here I could have thread A load and add, but then before thread A stores, thread B will load a stale value, and then it will add, and then it will store. So even though two threads are incrementing bins of B in this example, only one of them will succeed to do the increment, and the final value will be 1. And to solve this problem, what we typically do on a CPU is we use mutual exclusion, where we guard our increment using a lock. So we do mutex lock to acquire a lock, do the increment, and then release the lock. But we said that the problem with doing locking on the GPU is that whenever we mix locks with SIMD, we can cause deadlock. So for example, if I have thread 0 and thread 1 are in the same warp and they both try to acquire the same lock, one thread acquires the lock and thread 1 cannot acquire the lock. So thread 1 sits there waiting on this mutex lock operation for thread 0 to get the lock, but then thread 0 can't proceed because thread 0 is in the same warp and it's waiting for thread 1 to acquire the lock so that they can both proceed together. So to avoid this kind of situation, what CUDA provides is something called atomic operations, where we perform read, modify, write with a single ISA instruction. And that instruction is atomic add, and there are also atomic operations for all kinds of other operations like subtract, min, max, etc. So having said that, we saw how to implement histogram, but we saw that one of the problems with having all the threads each have one input and they all update the same histogram is we have a lot of threads that could be updating the same value, and they will all be executing atomic operations. And these atomic operations will take time for two reasons. One, that they're being done on global memory, and two, because there's a high probability that different threads will be accessing the same value, so they'll need to wait for each other. So the way we solve this is we use privatization, where every thread block had its own private copy of the histogram, and they would do the updates on the histogram. That way, threads in different blocks are no longer competing with each other. And then we do a final commit of the local histogram to the global histogram for each bin that is a non-zero. And if the histogram is small enough, we can even put the private copy of the histogram in shared memory so that we have a lower latency atomic operation. And then finally, what we saw is we can also apply thread coarsening, where each thread block takes a larger input segment. And what that does is that it results in us having fewer thread blocks, and therefore fewer local copies that need to be committed to the global copy. And therefore, we have fewer global atomic operations overall. So this is what we covered last time. And today, we're going to talk about a new pattern, which is merge. Before I start talking about merge, anybody have any questions about last time's material? Okay, so if not, then let's talk about merge. So merge, an ordered merge, is an operation that takes two ordered lists and combines them into a single ordered list. So for example, if I have these two lists over here, they can have different sizes, but they're both ordered. So here I have 1, 2, 4, 6, 6, 8, 9. Here I have 2, 3, 5, 7, 9. What a merge does is that it takes these two lists and combines them into a single ordered list. And the way to do and that list will look like this. And the way we do that is we bring in the 1, and then we bring in the 2, we bring in a 2, bring in, then next there's 3, so we bring in the 3, then we have the 4, and then we have the 5 comes in from here, the 6s come in from here, the 7 from here, 8 from here, 9 from here, and 9 from here. Okay, so this is what a merge operation does. And before we talk about how to parallelize merge, I first would like to implement with you a sequential merge. Okay, so let's go to the code in order for us to implement a sequential merge. So this is the code we're going to be using to implement merge throughout this lecture. And first, I have this this function merge sequential that does a sequential merge. So this function is going to take two arrays A and B, and it's going to merge these two arrays into an array C. And here I also have M and N, and M is going to be the size of the array A, and N is going to be the size of the array B. Okay, so how do we merge these sequentially? Well, what we're going to do is we're going to loop through these two arrays, and at each point in time, we're going to compare. We're going to have a counter that goes through the first array, a counter that goes through the second array, and each time we're going to compare the corresponding elements, and whichever element is less, we're going to add it to the destination array, and we're going to increment the counter for the destination array. This is how we're going to do it. So let's do that. So I'm going to start by declaring 3 counters. I'm going to declare unsigned int I equals 0. So we're going to use I to go through the array A. I'm going to have an unsigned int j, and I'm going to initialize that to 0, and I'm going to use j to index the B array, and I'm going to have an unsigned. I always mess up when I write unsigned. I'm going to write unsigned int k equals 0, and I'm going to use k to index the C array. Okay, and now what we're going to do is we're going to loop through these two arrays. So I'm going to use I and j to go through these two arrays. Okay, and I'm going to be merging. I'm going to adding the smaller value, and I will basically loop until one of these arrays is depleted, and then I will just store the rest of the values in the remaining array. Okay, so loop until either I finish going through my array A, or I finish going through my array B. Okay, so I will loop until while I is less than M, because M is the size of A. Okay, and J is less than M. So I'm going to loop until I reach the end of the A array, or I reach the end of the B array. Okay, and over here, what I'm going to do is I'm going to check. If the element in A is smaller, I'm going to put the element in A of A and C. If the element of B is smaller, I will put the element of B inside of C. Okay, so I'm going to check if A of I is less than B of I. Okay, then in this case, what I will do is I will put the A of I in K. So I'll write C of K is equal to A of I. Okay, so here, if my I is over here and my J is over here, and I find that A of I, which is 1, is less than B of I, which is 2, I will put 1 over here. And then what I want to do is I will increment the counter that points inside of array A. I will increment the counter that points inside of array B, array C. I won't increment this one because I will need it on the next iteration. Okay, so after doing C of K equals A of I need to increment K and increment I. There's actually a neat way of doing this in C++, which is where I think K++ and I++. So here, when I write K++, it means I use the old value of K and then I increment K. Here, when I write I++, it means I use the old value of I and then I increment I. Okay, now if A of I is not less than B of I, then what do? Then I need to put if A of I made a mistake here. This should have been B of J. Okay, so if A of I is not less than B of J, then that means B of J is a smaller value. that means I need to put B of J inside of C. So in this case, what I will do is that I will write else B of K is going to equal B of J. Okay, and then I want to increment, this time I want to increment K and J, not K and I. And I can do that the same way I do a post increment. So K++ and J++. So what this loop does is that it'll merge, it'll keep merging, taking the smaller element from each array until we reach the end of one of the arrays. Now, once we reach the end of one of these arrays, so somebody is asking me, why is it C of K++, not C of K? The reason it's C of K, well, C of K++ is the same as C of K, except that C of K++ will increment K after using K. Okay, so it is C of K. C of K is the element that we are going to be assigning, but after we assign to C of K, we're going to increment K. So this is what this does. Okay, so after we're done, this loop is going to end once we're done with one of the arrays, but we're still going to have the rest of the elements in the second array to store to C. So the way we do that is as follows. So if A is if we're done with B, but there's still some elements in A, what we'll do is we'll do while I is less than M, and then we're going to put all the elements of all the remaining elements of A inside of C. So we're going to do C of K++ is equal to A of I++. Okay, and then if it's the array B, that's the one that if we're done with A, but it was the array B, that's the one that wasn't finished. Then we're going to do the same thing for the array B. So we'll do while J is less than N. Okay, we'll do C of K++ is equal to B of J++. Okay, so this is how we do a merge sequentially. All right, is this clear to everyone? Any questions about this? Okay, someone's asking, is this efficient? Well, again, this is a sequential code right now. So this is our kind of our baseline code. This is sequential code, it's not parallel code. So we're talking about how to parallelize it next. But everybody understands the sequential implementation? Okay.
Yeah, doctor.
Yes.
The second part, the while I less than M, while J less than N, is it when ما سمعت امتى when you use it? Is it when the one of the arrays is done?
Right. So when we're merging these two arrays, we're going to reach the end of one of the arrays before we reach the end of the second array. Right. So here, the condition is going to the loop is going to exit either when we reach the end of A or when we reach the end of B. So if we reach the end of A, we still want to fill in the rest of elements in B. If we exit because we reach the end of B, we still want to fill in the rest of the elements in A. So that's why we have two tail loops over here.
Okay, thank you.
Yeah, you're welcome. Okay, so having implemented this parallel merge, the next question is, how do we parallelize this? Anybody have any ideas how we can parallelize this? This seems to be a very sequential thing. So how do we parallelize something like this? Any ideas?
Maybe we can do it in batches.
We can do some partial.
They do it in batches? What do you mean by do it in batches?
Send one thread per 4 elements, and each thread sorts those 4, and then puts...
So do you mean every 4 elements of A? Or remember, we're not sorting, we're just merging 2 sorted arrays. So do you mean sorted, do I assign to 4 elements of A, or 4 elements of B, or 4 elements of C? What 4 elements?
I mean, like maybe 2 by 2, like 2 of A and 2 of B, and then...
Okay.
Oh no, actually, that I'm not sure.
But if we put it in 2 of A and 2 of B, how do we know the 2 of A even correspond to the 2 in B? Maybe the first 10 elements of A should go first before any of the elements of B go first.
Oh, right, I know, that's why I said batches. Like maybe we can do it incrementally, and eventually all the elements drift in the correct locations if we do like something that converges. But
Okay, but then how would we do the parallel?
Right, yeah,
For-
I know.
The way to do it is probably to the execution of this code looks maybe like kind of or what we're doing looks kind of like a tree. So if we break up the array in multiple parts, we'll have kind of segments that we can parallelize for each one.
So which array do you want to break up into multiple parts?
Not so. You have one. So you have one array. So you start with one array. You break it up in half. Then you do this kind of like recursively, but not at the GPU level. On the CPU level, you recall the kernel every time you break the array in two.
Which array do you want to break into? Remember, we have two arrays. We have an array A and we have an array B, and we want to merge them. So which array do you want to break in half? A or B or C?
A and B.
So if I break A in half,
we
that does not necessarily mean I have a kind of an even split in B that corresponds to the halves of A, right?
Can we assume
Maybe
Professor?
maybe the entire array A comes before the entire array B.
Professor, I would say keep the shortest array like whole, like don't divide it, and take like one thread per element of the other array, and then try to compare it with all elements of the array that you kept intact. I don't know if that's efficient, but
Okay.
that way you're guaranteed like.
So I see where you're headed. I see where you're headed.
can we assign
go ahead.
a thread to each element of A, and then in the thread use it to find where it should appear in B? Then we have like indices.
Okay.
Now if we're actually putting them there, I'm not exactly sure, but we can find their positions.
Yes, so you're definitely headed in the right direction. So what you're hinting at is somehow we need to maybe partition. You have a partitioning where we find an element in A, and somehow we need to find the corresponding part of B, so that we can do different smaller merges in parallel. Okay. So I think a lot of you are kind of hinting towards that direction, and we will do something along these lines. But however, we're going to do something different. So far, the whole time we've been. By the way, this is the sequential merge we wrote. Now we're going to think about parallel merge. So far we've been whenever we've been parallelizing things, we've been thinking about partitioning the input. But this time, it actually makes more sense to partition the outputs. Let's take a look about. Well, a lot of times the input and the output directly correspond to each other. But for this particular application, it actually makes more sense and gives you better load balance if you partition the output. So here is how we can parallelize merge. Let's say, again, I have my array A that has size m, and I have my array B that has size n, and I have my destination array C that has the size m plus n. Okay. Now, one way to parallelize this is, a lot of you have been saying, why don't we partition A evenly across threads, and then each thread in A goes and finds the corresponding part in B, and then somehow merges those. We can do that, but if I partition A evenly, a small segment in A could correspond to a very large segment in B, or it could correspond to a tiny segment in B. So that work will not be distributed evenly across the thread. If I want to have a better distribution of work across threads, ultimately what I want is all the threads to merge the same number of elements, and the number of elements a thread merges actually corresponds to the number of elements the thread is going to write to C. So in this case, it really makes more sense to partition C. So the way we will parallelize merge today is we're going to take our C array and we're going to partition it into segments, and each thread will be responsible for one of these segments. Okay, so each thread will take a segment and we'll be responsible for sequentially merging the elements of A and the elements of B that are supposed to come to this segment. Okay. Now, if we partition C into segments and divide it across threads, the key challenge becomes, how does each thread find the corresponding elements in A and B that it needs to merge? Okay, so the key challenge is, how does each thread find the input segments corresponding to its output segments? So this thread that's responsible for this blue segment of C, how does it find the corresponding elements in A? It could be that and the corresponding elements in B. It could be that it needs 2 elements from A and 3 elements from B. Or this other thread is using 4 elements from A and 1 element from B. And a thread doesn't really know, how this second thread cannot wait for the first thread to finish its own merge for it to start its merge. Otherwise, there's no point in parallelization. So the key challenge is, given if I assign a thread to a certain segment, how does this thread find the corresponding segments in A and B? Somebody want to say something?
No, I was gonna say, maybe if we privatize it, but it doesn't make sense in this case. No, it's not.
Yeah, so privatization is an optimization we discussed. So here, yeah, you're right. Here, privatization is not very relevant. Okay, so let's take a look in more detail about what we're trying to do here. So each thread has the start index and the end index of the segment that it needs to merge, and it needs to find the corresponding index in A and in B. Given an index K into this array C, the output array C, what I want to do is I want to find the index I into the array A and the index J into the array B that correspond to the values that need to be merged into the segment starting at K. This is what I need to find. Okay, so given a K, we need to find I and J on this diagram, and we refer to I and J as the co-ranks of K. Okay, so when I say what is the co-rank of K in array A, that's I. What's the co-rank of K in array B? That's J. Okay, so the question is, how can we find I and J given K? Well, first we observe that K is equal to I plus J, right? The number of elements before K in the array C is going to be the number of elements before I in the array A plus the number of elements before J in the array B, right? So therefore, we know that K is equal to I plus J. And since we know that K is equal to I plus J, then it's enough for us to find I, and then since we know K, we can find J. Okay, so it is sufficient for us, given K, it is sufficient for us to find I, and then we can just find J by doing J equals K minus I. All right, so then our objective now is, given K, how do we find I? Okay, and then we can find J by simply doing J equals K minus I. Okay, so given K, how do we find I? Well, let's first start by setting a bounds on I. Okay, let's start by setting a bounds on I. What do we know about I? Well, first of all, we know that I is going to be an index into the array A. Okay, so what are the bounds on I? Okay, so let's start by setting
0 to m minus 1.
Sorry?
0 to m minus 1.
0 to m minus 1, right. So I is going to go from 0, I is going to be greater than or equal to 0 or less than or equal to m. Notice it can be equal to m. Why can I be equal to m?
If the value is not, it doesn't, I'm not sure.
Because we're doing I plus plus at the end.
Well, no, so in this diagram, I could have a K where I is equal to m, meaning so if I was m minus 1, then I is going to point over here to this element. When I is equal to m, where does I point?
It means
to the
all
end
the
of the
elements.
array, right?
The end of the array. So
exactly.
It doesn't belong to the first array.
Right, exactly. So I could be equal to m if in my last, or in one of these segments, I've reached the end of the array M and all the end of the array A, and all the elements are coming from the array B. Okay, so we know that I is going to be greater than or equal to 0 and less than or equal to M. So this is one bound we have on I. We can put another bound on I, and the other bound is based on the observation based on what we know about J. What do we know about J? What are the bounds on J? Well, similarly, J has to be greater than or equal to 0 and less than or equal to N. Okay, and we also know that J is equal to K minus I. So then K minus I is greater than or equal to 0 and less than or equal to N. Okay, and if we move K, if we subtract K from all these locations, then we know that minus I is greater than or equal to minus K and less than or equal to minus K plus N. And if we invert everything, then we know that I should be greater than or equal to K minus N and less than or equal to K. So we have these two bounds on K. We know that I is greater than or equal to 0, and also I should be greater than or equal to K minus N. So then the lower bound on I is the maximum of 0 and K minus N. And we also know that I should be less than or equal to M, and I should be less than or equal to K. And therefore, the upper bound on I is going to be the minimum of M and K. Okay, so the bounds on I is the maximum of 0 and K minus N, and the minimum of M and K. Is this clear so far? Any questions? Okay, any questions about how we about this bounds on K? Is this clear to everyone? All right, great. So having placed a bound on I, okay, so now we have a bound on I. We know that it's between this value and this value. The next step is to find I. Okay, so we have a bound on I. Now we need to find I inside of this bound. And what we can do is when we have a bounds on something, okay, and we have some kind of ordering inside of our array, you know, what does this sound like? And we want to search for some value, you know, what does the starting sound like?
Binary search or search?
Right, exactly. If I have a sorted array and I want to search for a value, okay, then what we can do is we can do a binary search. Okay, so what we can do, having established a bound on I, what we can do is we can perform a binary search for I inside of this array. Sorry, inside of this bound. Now the question is, how do we know that we have found I? Okay, so if I start at this bound and I do a binary search, how do I know when I have found I? Right, I'm not looking for a specific value here. Well, what do we know about I? What is I here? Well, I is the corank of K, and what that means is that all the elements before I should be less than all the elements after I, obviously, but they also should be less than all the elements after J. And we also know that all the elements after I should be greater than all the elements before I, obviously, right? We don't need to check this. This is given by the fact that A is sorted. But they also, all the elements after I also need to be greater than all the elements before J. So how do we know that we have found I? Well, we know that we have found I when A of I minus 1 is less than or equal to B of J. So A of I minus 1, this element, is less than or equal to B of J, which is this element. Okay, so the element here should be less than or equal to the element here. Why? Because the element here is going to be over here in this segment, and the element here is going to be part of this segment over here. So necessarily, the orange elements should be less than or equal to the green elements. So the A of I minus 1 should be less than or equal to B of J. And similarly, we know that B of J minus 1, so this element here, should be less than or equal to A of I, so this element over here. So these are the things we know about I, so we can use these things to determine when we have found I. Once we find the element that meets both of these conditions, it means we have found I. Okay? Note that one of these conditions is not enough. It's not enough for A of I minus 1 to be less than or equal to B of J. Okay, we also need B of J minus 1 to be less than or equal to A of I. Okay, otherwise, this element way over here, right, is going to be less than the element way out here. Okay, but that doesn't mean we found I, because the next element is also less than the previous element. Okay, so we can perform a binary search within this bound to find the element, to find I that meets this criteria over here. Okay, now when we do a binary search, it's not enough for us to find, to know whether we have found our element. What do we also need? We need a way of knowing whether our guess is, we need a way to know that our guess is correct, but we also need to know if our guess is what?
We want to know if we overestimated or underestimated some kind
Right,
of order.
exactly. Exactly. So we need a way of knowing not just if our guess is correct, but if our guess is too high or too low. Okay. So we're going to perform a binary search within the bound. We know our guess is correct based on this condition: if A of I minus 1 is less than or equal to B of J, and B of J minus 1 is less than or equal to A of I. Okay. What if our guess is too high? So our guess is too high. So this I prime over here is an example of a guess that is too high. Okay. So if our guess, if I prime, the guess for I prime is too high, that means the guess for J prime is going to be too low. Okay, and in this case, which one of these conditions is going to fail? How do we know that I is too high?
Because A of I prime
The
is
second
greater than
condition.
B.
Actually, the first condition. So the second condition is the first condition is the one that's going to fail, because A of I minus 1, which is this value, is not going to be less than B of J, which is this value. Okay, the second condition actually succeeds because B of J minus 1, which is this value, is going to be less than A of I, which is this value. Okay, so we know that our guess is too high if A of I minus 1, which is this value here, is not less than B of J, which is this value over here. Okay, or it's greater than it. Okay, or sorry, if it's not less than or equal to, so if it's greater than. So our guess is too high if AI prime minus 1 is greater than BJ prime. So if I prime is our guess, we know it's too high because we can check that AI prime minus 1 is not going is greater than B of J prime. How do we know if our guess is too low? So if our guess is too low, it's going to look something like this. Here, my I double prime is a guess that is too low. Okay, and in this case, my J prime is going to be too high. So how can I detect that my guess I double prime is too low? Well, basically, the second condition is not going to be met. Okay, so I know that here in this case, AI minus 1 is going to be less than B of J. But the way I know that this guess is wrong is that A of I is going to be less than B of J minus 1. Okay, so in other words, my guess is too low if B of J double prime minus 1 is greater than A of I double prime. Is this clear to everyone? Any questions? Okay, so then really the only difficult thing about merge is finding the corank. Okay, I divide, what I need to do is I divide my array C into equal parts and give them to different threads. Each thread has an index K, and then each thread needs to perform a binary search to find the corresponding I, and then naturally you would find the corresponding J, and then each thread would just do a sequential merge. And we already know how to do a sequential merge. It's obvious to how to divide an array into equal parts and assign a part to each thread. Okay, so really the most difficult thing about merge is doing this binary search to find the co-rank of k inside of the array A. All right. So to do that, what we will do is we're going to implement a co-rank function. All right, that takes a k, an array A, and array B, their sizes, and a value k, and finds the I and the j that correspond to this k. Somebody's asking, what if both of these conditions fail? Well, if both of these conditions fail, it means that our guess is correct. Okay, if this is false and this is false, that means this is true. Okay.
Professor, isn't divergence through the roof? Like the
Oh, yes, you're absolutely right. You're absolutely right. We will have divergence here because different threads are doing binary search, and they may take longer to find their result. So yes, you're right. This is going to suffer quite a bit from divergence. Yeah, but it's something that we have to live with if we want to parallelize something like that. Okay, so let's go and write the co-rank function that where given k finds I and j. I'm going to switch back to my code. I already have the signature for the co-rank function specified here. It takes an array A and array B, the sizes of A and B, which are m and n, and it also takes the index k. Okay, notice we don't need C over here because we're not using anything. C has not been generated yet. Okay, so we just need the index k into C, and we need to return the index I into A. Okay, so let's do that. So what we will do is we need to first set a bound. We're going to do a binary search. So we want to set the bounds, okay, and then initialize our guess to the middle of the bound, to halfway in between the bounds, and then start doing a binary search. So let's first find the bounds on I. Okay, so I'm going to write unsigned int. I'm going to define I low to be the lower bound on I, and we said that the bound on I is the maximum of 0 and k minus n. Okay, so in other words, if k minus n is greater than 0, then the maximum is going to be k minus n. Otherwise, the maximum is going to be 0. Now, one thing to keep in mind here is that k is an unsigned int and n is an unsigned int. So if I do an unsigned int minus an unsigned int, if n was actually greater than k, then k minus n is going to wrap around. It's going to be a very large number. So for safety, it's better to, rather than writing k minus n greater than 0, we should write k is greater than n. Okay? Okay, so now we have a lower bound on I. Let's also set our upper bound on I. So our upper bound, we're going to write unsigned int. We're going to call it I high. And I high is going to be equal to what? Well, let's go back and take a look. So here, the upper bound is the minimum of m and k. All right, it's the minimum of m and k. So the lower bound is going to be if m is less than k, then it's going to be m. Else, it's going to be k. Okay, so now we have a lower bound on I, and we also have an upper bound on I. Now what do we do? Well, we're going to do a binary search. Okay, so here we're going to start our binary search. We're going to loop. We're going to keep looping until we find our results. Once we find our result, we will return it. So that's why we're just looping, doing while true. Okay, and we're going to initialize first our guess. What's our guess going to be? Well, our guess I is going to be in the middle of the bound. So it's going to be I low plus I high over 2. Okay, and consequently, what's our j going to be? What's our j guess going to be? Remember, we know j
k
is
minus
always
I.
equal to k minus I, exactly. So then our j is going to be equal to k minus I. All right. So now that we've made a guess on I and j, now what we need to do is we want to check Is our guess correct? Is it too high or is it too low? Okay, so first let's check if our guess is too high. If our guess is too high, it means that a of I minus 1 is going to be greater than b of j. So we're going to check if a of I minus 1 is greater than b of j. Okay, so if a of I minus 1 is greater than b of j, it means my guess is too high. What do I do in this case? So here, if my guess is over here, it's I prime, right? It's too high. What do I do? In binary search, if we guess too high, what do we do? We're gonna narrow the bound, and then we're gonna guess again. Okay, so if my guess is high, what I will do is I will lower my upper bound. So I found a new upper bound on I, so I'm going to write I high is equal to I. Okay. Now, one thing to note is that I need to actually make sure that these axes are legal. Okay, I need to make sure that I minus 1 is going to be within bounds. I need to make sure that b of j is going to be within bounds. Because here, the way I got j is by doing j equals k minus I. Okay, if I was kind of a low guess, okay, j could have gone out of bounds over here. So I need to make sure that j is within bound, okay? And then I also, since I'm doing a of I minus 1, if I over here was 0, I need to make sure not to access I minus 1. Okay, so before I do this, I actually need a few other checks. I need to make sure that I is greater than 0. Okay, obviously, if I was 0, then my guess cannot be too high, right? Because I can't go lower than that. So I need to make sure that I is greater than 0 to make sure that when I access a of I minus 1, that's within bounds. And I also need to make sure that j is less than n in order to make sure that when I access b of j, I'm also within bounds. And again, j is less than n because if I is too low, then j could be too high. It could be out of bounds over here. Then if j was out of bounds, then obviously my I is not going to be too high. Because if I make it lower, that means I need to make j go even farther out, which is not possible. All right, so next, this is what happens if my guess is too high. If my guess is too high, I set a new upper bound. Okay, and then in the next iteration, I will find a new guess that is within that bound. If my guess is not high, now I need to check if my guess is too low. If my guess is the way I check if my guess is too low, I check if b of j minus 1 is greater than I. So here I'm going to check else if b of j minus 1, okay, it says b of j is greater than I. So if b of j minus 1 is greater than a of I, okay, in this case, what does that mean? It means my guess is too low. So in this case, I found a new lower bound. So I will set I low is equal to I. And similarly, when I perform these axes, I need to make sure that I am within bound. Okay, so if j was 0, okay, then I need to make sure I'm not accessing a value that is out of bounds. So here I should check that j is greater than 0 to make sure that my access to b of j minus 1 is valid. And I also need to check that I is within bounds of a. So I need to make sure that I is less than m. So I had I less than m. Okay. So in this case, this means my guess is too low. All right. Clear so far? And then finally, if neither of these succeed, if my guess is not too low and my guess is not too high, that means my guess is correct. So in this case, my guess is I, so I simply return I. Okay, so this is the corank function. It takes a and b and their sizes. It takes k and it finds I that corresponds to this k over here. Okay, and we simply return I. Okay, so having implemented this corank function, what we still need to do is we need to implement the merge operation itself. Okay, we need to implement the merge operation itself. Well, the merge operation is quite easy, right? I simply divide my array C. Okay, I find K for each thread. I call the corank function to find I. Okay, and then I just do a sequential merge. So let's implement that. So I'm going to come down here. Okay, so here I've already defined I want this many elements per thread. I just have 6 elements per thread, for example. Okay, I'm going to have 128 threads per block. So the number of elements per block is going to be the number of elements per thread times the number of threads per block, obviously. And then down here, I've done the code that does the allocation and calls the kernel with the appropriate number of threads per block, and then also, divides the total array size by the number of elements per block. Notice that the number of elements per block is different from the number of threads per block over here. Okay. Now let's back up. So here in the merge kernel, what we want to do is first we want to identify the K for each thread. How do we do that? Well, we find the thread index. Okay, thread 0 is going to be responsible if the elements per thread is 6, for example, then thread 0 is going to be responsible for element 0. Thread 1 is going to be responsible for element 6, which is 1 times 6. Thread 2 is going to be responsible for element 12 onwards, right? So the segment starting at element 12. Thread 3 is going to be responsible for the segment starting at element 18. In general, thread I is going to be responsible for the element starting at I times 6, or I times the number of elements per thread. So my K is going to be my thread index times the size of the segment that each thread is responsible for. Okay, so my K is going to be equal to my global thread index, so that's block x.x times block dim.x plus thread index.x times the number of elements that each thread is responsible for. Okay, so now we have the K for each thread. Now we've partitioned our output array such that each thread takes element per thread element. Okay, of course, we need to make sure that our K is within bounds as usual. So here the bounds on C is m plus n. So I need to make sure that, if I'm in the last thread block, I need to make sure not to do anything that's out of bounds. Okay, so I'm going to have a bounds check that makes sure that K is less than m plus n. All right. And then inside of this bounds check, what do I need to do? Well, I need to find I and j, and then I'm going to call the corank. Then I'm going to call the sequential merge. Okay, so how do I find I and j? Well, I wrote this corank function up here that finds I and j for me. So I'm simply going to call the corank function. Let's go back and see. So the corank function is going to take my array A, my array B, going to take m and n and k. So what I will do is I first want to find the corank of k. So I'm going to write I is equal to corank. Okay, this is a device function, so I can call it from inside the kernel. I is going to be equal to the corank of, I'm going to give it A and B and M and N and K. And it's going to do this binary search and give me back I. And then how do I find my J? Well, simply my J is going to be equal to K minus I. Okay, so I'm going to write unsigned int J is equal to K minus I. Okay. Now, before I call the sequential merge is also the sequential merge that we implemented also expects to find, it also wants the size of these two input segments, right? I need to know what is the size of the I segment, what is the size of the J segment. Okay, so how do I find the size of the I segment and the size of the J segment? I saw how to find the beginning. How do I find their sizes?
We can't find their sizes.
Well, let's think about it. The size of I, right, is basically where the segment for this thread ends, which is where the segment for the next thread begins. Similarly here, J, the end of J is where the segment for the next thread begins. So basically the size of the where this where this ends is going to be the co-rank of where this segment in C ends. And I know where this segment in C ends because I know K and I know how large the segment is. Okay, so to find the size of each of the input segments, I simply find the co-rank, as one of you did observe in the chat. We simply find the co-rank for the next thread. Okay, and we do that like this. We can, of course, we can do fancy things like check if the next thread has, try to talk to the next thread and tell it to give us our co-rank. But let's keep the co-rank that it found. But let's keep things simple. So what we're going to do is we're going to first find the K for the next thread. Okay, so we're going to write unsigned int. We're going to call that K next. So the K of the next thread is going to be our K plus the number of elements per thread. So K plus the number of elements per thread. However, it could be the case that I'm out at the very end and this last segment is not complete. So I need to make sure that K plus number of elements per thread is actually not out of bounds. It's not greater than m plus n. Okay, so if K plus the number of elements per thread is within bounds, so if K plus the number of elements per thread is less than m plus n, then my answer is going to be K plus the number of elements per thread. Okay, otherwise it's going to be m plus n. Okay, so now having found K next, how do I find I next and J next? Well, simply I can find I next by calling co-rank on K next. So I'm going to write unsigned int I next is equal to the co-rank. I give it A, I give it B, I give it M, I give it N. Okay, and I give it K next. All right. How do I find J next? If I know I next and K next, well, I simply use the J is equal to K minus I. So here I write unsigned int J next is equal to K next minus I next. All right. So now I have the beginning and the end of each of the input segments. And now I can just do a sequential merge. Now let's go back and look at our sequential merge that we implemented. So we've already implemented a sequential merge. It takes two arrays, two source arrays and a destination array. And it takes the sizes of the two source arrays, and it does a sequential merge. Can we reuse this? How can you reuse the sequential merge that I wrote for the CPU?
You just take m
Just
to be
have
I
to.
next.
Sorry?
We take m to be I next minus I and n to be J next minus J.
Right. So that's what we're going to pass to it. What I was referring to is I can make this a device function. That way I can call it from the device. Okay. So I'm going to convert this sequential merge that we originally wrote for the CPU to a device function. Okay. And you're right. We have to use host device if we want to use it on the CPU as well. But I'm actually not using this on the CPU. I'm just using it on the GPU. So we can just write device and that should be fine. Okay. And now I can pass to the merge function. I need to pass the two input arrays, the output array, and the sizes of my two input arrays. Let's call merge sequential from my thread. Oops. Sorry about that. So we're going to come down here to our thread, and the thread is going to call the sequential merge. It needs to give it the beginning of A, right? So what is the beginning of the input segment? Well, it's the address of A. It's A plus I, right? So it's the address of A of I. So give it the address of A of I. What's the beginning of the B segment? Well, it's going to be B plus J. So it's going to be the beginning of the element B of J. So I'm going to give it the address of B of J. Okay. What is the beginning of the destination segment? Well, it's going to be address of C of k. It's going to be here. So I'm going to give it the address of C of k. Okay. Now I need to give it the size of my input segment. Well, the size of my input segment is basically I next minus I, right? So I'm going to give it I next minus I. And I need to give it the size of my second segment. Well, that's going to be J next minus J. So I'm going to give it J next minus J. Okay? So really the most difficult part of parallelizing merge was writing this corank function that finds the corresponding I, corresponding J. The rest of that is simply calling the sequential merge that we already wrote for the CPU. Is this clear? Any questions? Okay, well then let's compile and run this code and verify that it works. I'm going to compile this. Okay, and we will run it. And indeed, the code works. And as you can see, we got quite a bit of speed up compared to the CPU time. Right? You have 13 milliseconds on the CPU, 2.7 milliseconds on the GPU. Obviously, this is a very memory-bound kernel. Okay, because all we're doing is loading data from memory and comparing it and storing it to memory. We're not doing any floating point operations here. So obviously, we don't expect the GPU to be kind of have a huge amount of performance improvement compared to the CPU, but this is still a decent amount of performance improvement for something, and we haven't even optimized this yet. Okay. Now, of course, if you include all the copy time, right, the GPU is slower. So obviously, you're not going to send two elements to the GPU just so that you can merge them. But if something is already on the GPU and you want to merge it, it's definitely worthwhile doing it on the GPU because the GPU is faster than the CPU if you don't include the copy time. All right, is this clear to everyone? Okay, speaking of performance and optimizations, let's take a look at how we can optimize this. So this is the parallel merge code that we wrote. So one thing that you guys have observed is that we have divergence. There's another big problem here, which is when we do all this binary search on these arrays. So here, when I'm doing all this binary search on my global memory arrays, and here I'm doing all this binary search and accessing these arrays. Why is that bad for performance? Imagine each thread here has a different value, and each thread in the block, one thread is going to have a guess, another thread is going to have a completely different guess somewhere else, and they're all going to bounce around inside of our global memory arrays. Why is that bad?
It's not coalesced.
Right, exactly. Our coalescing here is very bad. So what can we do to improve our memory coalescing? So if I have uncoalesced accesses to global memory, one of the optimizations I can do is I can load the data to shared memory in a coalesced way, and then do all the uncoalesced accesses inside of shared memory. Okay, and this is what we can do. So let's. So here, one observation is that our memory accesses are not coalesced, because during the corank function, each thread performs a binary search which has random access. So binary search has random access, and then each thread is accessing a completely different location during that random access, so that makes things even worse. So during a sequential merge, each thread loops through its own segment of consecutive element. Okay, so when I actually finish the corank function, let me go back here. When I finish the corank function and I'm doing a sequential merge, one thread is looping through these, another thread is looping through these, another thread is looping through these. Okay, so even after I finish my binary search, which has random access, my accesses are not coalesced because the threads are looping through different places in my input. So one optimization that we can do is we can find the segment for the entire thread block. We load the entire block segment to shared memory, and then we load our loads, and this way the loads from global memory are coalesced. So we load the entire block that the thread block owns to shared memory, and that way the loads are coalesced. Okay, And also, if we are only finding the segment for the entire block, that means only one of the threads in the block needs to do the corank function. I don't need to do corank for all the blocks for all the threads in the block in global memory. So I do one corank to find the whole block segment. Okay, I load that, only one thread in the block does the corank to find the block's input segment, and then I load it from global memory in a coalesced way. And then each thread will do a corank inside of shared memory in order for it to find its subsegment that it owns, and then it will do the merge in shared memory to provide a result array in shared memory. And then we can take this result array and then store it back to global memory in a coalesced way. So here the non-coalesced accesses will be performed in shared memory. Let me show you an illustration of what I mean by that. So here, if I have many thread blocks, rather than each one of these threads finding its segment inside of C and doing a binary search in the global memory arrays for A and B, what we will do is we will only find the corank for each block. So each block is going to have a K block. So here the first block owns this entire blue segment. The second block is going to own this entire yellow segment. The third block is going to own this entire green segment. One of the threads in each block is going to find the corank for that block segment. Okay, and then so here for this middle block, we have this K block over here. So we find the I for the block and the J for the block. And then what we can do is that the threads inside of the thread block can collaboratively load all of this segment and all of this segment into shared memory. Okay, so each thread block, the threads in each thread block will load the segments for that thread block from global memory to shared memory in a coalesced way. Okay, and then now that all these threads have collaborated to load A and B into the A segment and the B segment into shared memory, now what can happen is that these threads can each identify what segment within AS and BS they're responsible for and merge those segments. So here I have an array C of S that I'm going to also put in shared memory. Each thread is going to have be responsible for its own output segment inside of C of S. And then what the thread will do is that it will find the corank. So here, for example, I have 1, 2, 3, 4 segments. So this thread over here is responsible for this segment here inside of shared memory. So that this has a K. So what it'll do is it'll find the corank, which is I, and then each thread will merge its segments into shared memory. So this thread will merge this element and these two elements over here into shared memory to find the segment. And then once we are done, we will take this entire segment of C of S and store it in a coalesced way to global memory. Okay, so to summarize, we load the segments of A and B in a coalesced way to shared memory. We do all our binary search to find the corank for each thread inside of shared memory. We do the merge, which is uncoalesced, also in shared memory, and then we store from shared memory to global memory in a coalesced way. Okay, is this clear to everyone? Any questions about this?
Professor, we just need to do corank for the next block too to know where the block ends, right?
Yes, of course. So each block will have to do corank for itself and for the next block in order for it to find the total size of its segment and the sizes of the other segments.
Okay.
Okay, so I was actually hoping to implement this code with you in class and run it to show you how much performance benefit it gets. It actually does have quite a bit of performance benefit, but unfortunately, because we lost time at the beginning of class, we don't have time to implement this optimization together. What I will do is I will simply walk you through the code before we end. So here, this is the parallel merge with using tiling to improve the coalescing. Here, each thread block is going to find we're going to find the K for each thread block. This is K block in the previous diagram. Okay, and we'll do that by multiplying the block index by the number of elements per block. We also find the k for the next block. And then what we want to do is we want to find the co-rank for k block and k next block. However, we don't want all the threads to do this. We only want one thread in the block. So we want one thread in the block to find k block, to find the co-rank on behalf of all the other threads. So what we will do is we will declare I block and I next block inside of shared memory, and we will have one thread, in this case it's thread 0, we'll find the co-rank for I block and I next block. All right, and then after we do that, we will sync threads. Yeah, of course, there's a whole bunch of optimizations you can make. Maybe you can have two different threads. One of them finds the co-rank for I block, one of them finds the co-rank for I next block, right? I'm not getting into all these other optimizations for the sake of time. But we basically find the co-rank for I block and I next block. And we sync threads. This way, all the threads wait for thread 0 to find the co-rank I block and I next block and puts them in shared memory. Okay, and then after we sync threads, each thread is going to also find J block and J next block by simply subtracting I from K. Now all the threads have J block. All the threads have know where the block segment starts. So now the threads can collaborate with each other to load the A segment. Okay. So here, every thread, here I equals thread index.x, and we skip by block index every time. So here the threads collaborate with each other to load the A segment into shared memory. Okay, and then we're going to use the same array rather than declaring two arrays in shared memory. Right, we're going to use the same array wherever, because we know that the total number of elements in both A and B is going to be the number of elements per block. So rather than creating two arrays with that upper bound, we can create one, and wherever A of S ends, we're going to have B of S begin. So here, the number of element M block is going to be the number of elements in the A segment, and then the B segment is going to start after the A segment, and then we're going to continue by loading the segment of B in a coalesced manner and putting that in shared memory. Okay, so now we have the A segment and the B input segment inside of shared memory. Of course, we sync threads to make sure that all threads are done loading the segment to shared memory before we end. And of course, notice how here these axes are coalesced, because here, I is thread index I varies with thread index.x, and that's what we're using. I block is constant for all the threads in the block. Same thing over here. Okay, after we do that, what we do is we declare another array in shared memory. That's for C. Okay, every thread is going to determine its segment within this array, and then every thread is going to find the co-rank of its segment within the array, and it's going to do a sequential merge. And then after we're done, now we have our merged arrays in C of S. What we will do is we will write out the result from shared memory to global memory in a coalesced way. Okay, so this is the code. Again, I apologize that we don't have enough time to implement it together and test it out because of the time that we lost at the beginning of the lecture. Any questions? Okay, well, if there are no questions, then you can read more about what we covered today in chapter 11 of the textbook. And that is all for today, and I'll see you next time. Bye, everyone.